Temperature coefficient for capacitors. The temperature coefficient indicates the amount and the direction of a change in capacitance value with temperature. And this is not uncommon with electronic components. Most electronic components have some temperature coefficient associated with them. The thing to remember always with electronics is heat kills. When a device, whether it's a capacitor, whether it's a resistor, whether it's a transistor, your power supply, which is a macro level, as the heat increases, the efficiency of the component decreases. A positive temperature coefficient means that the capacitance increases with an increase in temperature or decreases with a decrease in temperature. Negative temperature coefficient means the capacitance decreases with an increase in temperature or increases with a decrease in temperature. So the thing to remember is that when these things are operating, when current is flowing to them, when the circuits are active, you are going to have heat in the circuit, and the device will start performing differently. Leakage is normally an internal aspect. No insulating material is perfect. The dielectric of any capacitor will conduct some very small amount of current. Thus, the charge on a capacitor will eventually leak off. Some types of capacitors, like a large electrolytic type, have higher leakages than others. An equivalent circuit shown in figure 12.4 to the right shows a typical modeling or schematic, if you will, of a capacitor, which includes its leakage resistance, a pathway for the current to flow. Physical characteristics of a capacitor. You can see by the diagrams below in 12.5. The parameters are important in establishing the capacitance and the voltage rating of a capacitor. Plate area, plate separation, and the dielectric constant. So any of these three is going to change the characteristics or the capacitance. Plate area, the capacitance is directly proportional to the physical size of the plates as determined by the plate area. So you can see that these two are completely lined up. If we start to move the plates, we start changing the plate area and the capacitance for the device. If the plates are moved in relation to each other, as shown, the overlapping area determines the effective plate area. Plate separation, how much distance between the plates or how much dielectric distance we have between the plates will determine the plate separation. Capacitance is inversely proportional to the distance between the plates. The plate separation, then designated D. A greater separation of the plates produces a smaller capacitance. As previously discussed, then the breakdown voltage is directly proportional to the plate separation. The further the plates are separated, the greater the breakdown voltage. Dielectric constant. What is the material between the plates and what is the constant related to it? Well, it's based on the material. As you know, the insulating material between the plates of a capacitor is called the dielectric. Dielectric materials tend to reduce the voltage between the plates for a given charge and thus increase the capacitance. If the voltage is fixed, more charge can be stored due to the presence of a dielectric than can be stored without a dielectric. The measure of the material's ability to establish an electric field is called the dielectric constant, or the relative permittivity, symbolized by the Greek letter epsilon. Epsilon R is the relative permittivity. Capacitance then is directly proportional to the dielectric constant. The dielectric constant then of a vacuum is defined as 1, okay, that's your perfect condition, and air is considered to be very close to 1. The values are used as a reference, so we're going to reference that with actual materials. So other materials have values of epsilon R and are specified with respect to that of a vacuum or in air. So, for example, a material with a relative permittivity epsilon r equal to 8 can result in a capacitance 8 times greater than that of air, with all other factors being equal. And we can see in the diagram some examples here of materials and their typical relative permittivity. The dielectric constant, relative permittivity, is a dimensionless unit because it's a relative measure. As we've seen in most other things, it's a ratio. It's a ratio of an absolute permittivity of the material, epsilon, to the absolute permittivity of a vacuum, epsilon naught. And it's expressed as epsilon over epsilon naught, giving us the unitless dimension then of epsilon r. The value of epsilon naught then is 8.85 times 10 to the minus 12 farads per meter. Again, another value and another relationship that you need to keep track of and put in your notebook. So as we start applying this, then all these measures like permittivity, we can see that we can determine the capacitance by a mathematical relationship. So we've seen how capacitance is directly related to the plate area, A, and the constant, dielectric constant of epsilon r, and it's inversely related to that separation between the plates. So a formula for calculating the capacitance in terms of these three quantities is the area times epsilon r, which is 8.85 times 10 to the minus 12 farads per meter, divided by the distance between the plates. If you look at an example, determine the capacitance of a parallel plate capacitor having a plate area of 1/100th of a square meter and a plate separation of half a mil, 1.27 times 10 to the minus 5 meters. The dielectric is mica in this case, which has a dielectric constant of 5. So now it's just a matter of putting the values into this relationship for solving for the capacitance. And you can see as we put the plate area, epsilon r times 8.85 times 10 to the minus 12 farads per meter divided by 1.27 times 10 to the minus 5th distance in meters, we get 0.035 microfarads. Okay, so calculating the capacitance then of a basic ideal capacitor. So when we come back, we're going to take a look at the various types of capacitors. Capacitors are normally classified according to their dielectric material and whether they're polarized or non-polarized. That's something you'll have to keep track of. The most common types of dielectric materials: mica, ceramic, plastic film, and electrolytic, which is an aluminum oxide and tantalum oxide. So we're going to look at how the capacitors are distinguished and characterized based upon the material that we find in our capacitors.